大時計です。高尾山大峠峠。さあ、どっちや？
Your chest is thumping with the rocket's vibrations, and you know that you just spent 6-7 years building this really delicate, complex machine, and viscerally you're like watching it blast off on this controlled into space. And not only is it just terrifying, but you really get this sense that you're sending something away from Earth when you see a rocket launch with your own eyes. So go do that sometime. There's a lot of good launches these days, including from Vandenberg down in California.
風の部屋は残念だったな。
And one of the things that we were able to find almost immediately was thanks to this crazy landing system. So these rockets were firing from the jetpack, and even though that jetpack stayed something like 40 feet off the ground, the jets created little areas that scoured away the local sand and gravel and exposed bedrock below, which was pretty cool, because if you're a geologist, you don't really like sand and gravel, you don't know what it is or where it came from. You like bedrock. Bedrock means that rock is there. It means it formed there, and it tells you something about it. And so the fact that we landed on this big gravelly area, but within these scours we had rock, of course, the very first thing we did was go check out those areas. And there actually was kind of a gold mine. You heard this alluded to at the end of that video. There's a couple spoilers in there of what we found the first year, but what we found was these slabs of bedrock that were some places buried underneath the soil were eroding. And as they were eroding, we realized the slabs were made out of a bunch of little rocks cemented together. And those little rocks were falling out in collections. This is probably a billion years of erosion. And the rocks themselves were rounded. And rocks don't really get rounded through many natural processes other than the most effective one on Earth is transport in a stream. Like pebbles just rotating and sliding with one another in a stream bed. You can get, if we measured all the angles of the rocks, exactly how rounded they were, the size of the rocks, compared them to different places on Earth, and it told us that we were actually driving through an ancient stream bed on Mars that probably had transported these pebbles for something like 10 to 15 miles. And the water was flowing somewhere between sort of ankle deep to hip deep. So it's a pretty good sized stream, maybe even a river. For people who had seen for maybe a couple of decades, like me, rivers on pictures of Mars from orbit, you sort of know that these things exist. But when you're there and you're seeing the rounded pebbles and you think, man, we were driving right through an ancient stream bed, that just brings a whole new meaning to it. And so this is the first time we really were able to find this evidence of that water flowed on the surface of Mars in a pretty vigorous way. We went to a place where that water may have collected into a lake, and our hypothesis was that this flat area here, you can see how different it is now. The gravel's all gone. It's just a flat plain of rock that very much looks like it could be an ancient dry lake bed. And so we drilled into it. This is the first time we got out the drill. Here we are drilling in a place called Yellowknife Bay. Here's what it looks like when we drill. We end up with a little dime-sized drill hole. And if you can see these little black dots here, those are the laser places. We blasted with a laser. So we're looking down with Curiosity from about 7 feet off the ground, firing our laser into a dime-sized drill hole, and making that little pattern down the side. So it's a pretty fantastic machine. And with the laser, we could then see if the composition of the rock changed as we drilled about 6.5 centimeters, about 2 inches into the surface to gather the powder. What's cool about this picture is that we drilled the rock, and then we took this picture at night, using our own LEDs, our own lights at the end of the arm in the middle of the night. And what's neat about that is that Mars is very dusty. So any picture you take during the day always has this orange cast to it because the sunlight's very heavily focused. It's like a very foggy day on Earth. But if you wake up in the middle of the night and take a picture with your own light, you can actually see what color Mars is for the first time. So this is like a true color picture of Mars, and it's, no surprise, it's orange. It's just not as orange as it looks in the middle of the day. And what's really cool is that the powder that we drill is not orange, it's gray. And so the skin of Mars is all oxidized and rusted, but you just drill a few inches into a rock and you can get more pristine material, which is a very good sign for one day finding evidence of life, because it means that the environment that's now changing Mars today hasn't penetrated that deep into the rocks where things could have been living at one point. And it would have, it could have destroyed all that evidence through the oxidation that's occurring at the surface. So what did we find? Here's a couple of pictures that show you the kind of data that we get. We drill into the rock and we put it in the material into some laboratories, and one of the laboratories takes an X-ray and shines that X-ray through the rock powder. It's called an X-ray diffractometer. Diffraction is a fancy scientific word for splitting light into different wavelengths, like creating a rainbow when you shine light through a prism. We do that just with X-rays, and the reason that you get these rainbow arcs when you shine X-rays through rocks is that the rocks are made out of crystalline minerals. So every mineral is a kind of crystal that diffracts the X-rays in a different way. And so a scientist can read these arcs like a fingerprint, the spacing of the arcs, the intensity of the arcs, and tell you exactly what minerals are in those rocks. And if we find clay minerals, like we did, this big arc down here is called phyllosilicate. That means basically a clay. And so we found clay minerals in this hypothesized lake bed, which tells us that water was actually here, and it actually probably was a lake bed. The other experiment that we have, the other laboratory we have, is a gas chromatograph mass spectrometer, which means it's a very common instrument you'd see on all the detective TV shows. It's the kind of thing that tells you element by element what's in a sample. And the way we get the material out into the instrument is you put the powder in the laboratory and you bake it. And you bake it at about 1,000 degrees. And as you do that, the rock starts to degrade. And as the rock degrades and you're slowly ramping up the temperature, different minerals decompose at different times. And so this time is running left to right. And so a bunch of water comes off first, because water is pretty easily removed when you heat something. And then as you heat it up more and more, carbon dioxide comes off, oxygen comes off, other things come off. And so you can sort of reconstruct what was in the rock based on how it degraded as you heated it. And so these two pieces of information are sort of the core science we get from any rock sample. And they work in synergy with each other. We can detect clays both by the arcs it makes and by the fact that clays decompose at about 600 degrees and they release a bunch of water. So we also found carbon, oxygen, hydrogen, sulfur, phosphorus, nitrogen, all those things we talked about earlier being important for all the cells in living organisms. We found evidence of liquid water, and we found sources of energy, because there were different. One example is there's different types of sulfur in here, which have different chemical states. For those of you who are chemists, there's reduced sulfur and oxidized sulfur minerals, and that's the kind of thing that a microbe can use to draw chemical energy from. So even at this very first site, in the first year of the mission, we found water, evidence of water. We found key chemical ingredients that life would require. We found sources of energy. So we found a habitable environment, which was fantastic. So that took a lot of pressure off us, frankly, because we were able to tell all the people who supervise us that we were able to successfully accomplish the goals of the mission in the first year we were on Mars at this first drill area. And that allowed us in the last 4 years to just add to that story more and more, knowing that we at least accomplished the basic elements of what we set out to do. So, we were driving to the mountain, we came across these, and there was more than one of these formations, and we studied it, and based on the evidence of finding the river before and the lake, and studying the sand up close and figuring out the sand particles were too big to have been transported by wind, must have been involved with being transported by water. We concluded that this formation was a delta. So here's a little cartoon of what we think is happening. Water is flowing here from right to left, and you have water flowing downhill into rivers. Then that water encounters a lake, and when you encounter the lake, that fast-moving river water all of a sudden slows down. So all the sand it's carrying and all the dirt it's carrying begins to fall out of the water. And so you end up with all these sand deposits, tilted sand deposits, right where the river meets the lake. And then as you go further into the lake, now all the silt begins to fall out, and you get these very fine layers of silt that build up at the bottom. That muddy stuff your feet get at the bottom of the lake is over here. So here's where you get your pebbles, here's where you get your sand, and here's where you get your mud. So we found the pebbles in the river. We drove a little bit closer to the mountain. We found the tilted beds of sand. Then, of course, our hypothesis was when we get closer to the mountain, we're going to find
こんにちは。
more lakes. Not the lake that we found out on the plains, but if the deltas are all facing the mountain, maybe the mountain itself is made up of lake deposits. And we got to the mountain, and I hope you can see this, but what you're looking at are slabs of rock. This is only about 2 inches across here, and the rocks are made up of extremely fine layers, just hundreds and hundreds of layers, about a millimeter thick each. And the entire mountain that we've driven up so far is made of just a continuous set of these millimeter layers. Now we've driven up about like 1,000 vertical feet that are made up of these tiny layers, and without much of a break in the continuity of the layers. And when you have these very continuous layers of mud-sized sediment, it's very consistent with the idea that this is all mud that formed maybe annually as lakes were fed by streams, and then hardened into rock. So how do you get a mountain where there once was supposed to be a bunch of lakes? Good question. So here's our idea, is that Gale Crater formed, and then back when Mars was a little more wet, and there was maybe precipitation, or at least groundwater. Groundwater flowed through all the cracks in the rock, and maybe fell out of the clouds, and formed lakes that filled up the crater. And the lakes maybe never were that deep, but sediment continually being brought in by the rivers, and that silt is settled out in these lakes, and slowly over many, many millions of years, built up millimeter by millimeter, and the lake rose as the mud kept getting thicker. And then over time, so imagine, like keep your eye maybe on this spot where imagine the rover is studying right there. Over time what happens is that a few things. So the lake level was 1
やっと下山できました。
and at some point this stuff that is not really lake, it's just maybe dust, filled it up even more, and then the climate of Mars changed in a way where no longer were things being brought into the crater, but now wind was scouring stuff out of the crater. And it scoured it out in a way that sort of dug this big pit into what was a crater at one point, leaving the dusty stuff here, and then the layers of lake sediment that we're now studying climbing up. So these lake sediments would have gone all the way across when the lake was filling it, but all this has been removed over eons by wind. So that's our story. We're sticking to it. And we're continually finding evidence to support it and making our case to the rest of the scientific community through the usual process, lots of peer-reviewed papers. But so far, when we run these ideas by Earth geologists who of course, can do a lot more advanced stuff than we can do on Mars, they think we have a pretty good idea of what we're seeing here. So, we've now driven about 18 kilometers, so 11, 12 miles, on the ground. We landed out here on the plains. This is a sort of map looking down. These are the plains we landed in. This is the mountain and all the layers of the mountain. So we landed out here. We made all those discoveries right where we landed at Yellowknife Bay. Then we drove pretty fast, found those deltas kind of in here. We got to the edge of the mountain about 2 years
風の上を回ったね。
and for the last 3 years, we've been slowly going up all the layers of the mountain, little by little.
高尾一周だな、今日は。
And we'd like to do this remaining section
10キロぐらい、20キロぐらい。
end. So hopefully we'll be able to do all this in the next 2 or 3 years. And once we get up to this layer, we will have studied all the layers on the mountain that appear to have formed. So far we've drilled 15 holes. Here's 12 of them. And you can
必ず土砂があるか
holes that the material is reddish when we drill it.
No,
So maybe the
yeah.
oxidation has penetrated into the rock. There's holes that are, most of them are pretty gray.
ら。葉っぱが全部土砂になると思え
We
ば
tend to find the clay
前
minerals
の真似土砂
and
が。
even organic molecules, very simple carbon-containing molecules that have survived because they haven't been oxidized and destroyed. And then we found a couple more red holes lately. I think the next few slides is a little bit more of a tour, just my favorite pictures. So, but just to give you another sense of the variety of things that we're seeing as we're driving along the last few years. Here is a nice picture showing 3 materials that we've gotten very used to seeing that are very different from each other. There's the first thing you see here is this pale bedrock that's very smooth. Those are the layers. And if you look at closely, this particular sandstone is very much consistent with being in and then the third thing you see here is not that interesting. Study them, and then we have to understand how this later stuff covered up
森林よくしてきた。
and how it's related.
やっぱ楽しいな、お父さんは事故されなければ。
This is one of my favorite pictures. These are the very several stories high, big buttes that we drove through. Like you're driving through Utah or somewhere, Bugs Bunny and Roadrunner country. And you're driving through here. These are those lake deposits, and again, the sandstone is above them. And the reason you get these buttes, whether you're talking about New Mexico, Utah, or Mars, is because the sandstone is a little bit more resistant to erosion. So even though most of it's gone, these layers used to connect at one point. The sandstone is a little bit of armor that the stuff is being eroded away. So you get these little towers. But eventually, another billion years, these will be gone too, leaving these lake deposits exposed. Here's the thing we saw at the beginning, the selfie. What's neat about this is we studied some of these modern sand dunes. It was actually the first time we've ever seen modern sand blowing around on Mars. The other rovers have seen ancient dune fields, but we actually were able to drive up to dune fields and watch them actually moving, which is really cool too. Even though it has really nothing to do with life and our main goals and mission, we're on Mars, you got to study it. And so we did some playing around, we dug some trenches, we watched sand avalanche, we watched sand blow, and one of the things we discovered was that, not surprisingly, there's a lot of similarities to sand dunes on Earth. The dunes have similar shapes.
これ一応タイツなんですけどね、ストッキングじゃないんですけど、タイツなんです。ちゃんと薄いというでもちょっとかっこ悪い。まあいいか、夏用だから。
but determined that it was an iron nickel meteorite, which is similar to iron meteorites we find on Earth. So that's neat. Here's a picture of a rock slab. This is about 1 inch here, where we see all this layer that we think are indicative of like ancient lake beds. But in this particular slab, they're all and they have these interesting shapes, and those shapes are very below an ancient lake on Earth, or even a current lake on Earth, where gypsum or other salts are crystallizing in the mud below the lake. And so we found these little swallowtail shapes that are very diagnostic of gypsum crystals, which is a kind of salt that forms in lake beds as they dry out. And these crystals are forming in the sediment. So yet another circumstantial piece of evidence that we are actually studying ancient lakes. On the opposite of the
一級河川南阿蘇と
but it seems that like in this picture, we found like this lake literally disappeared. So this is a slab of rock that's made out of mudstone that formed through the lake. Once pretty white mud that hardened into rock. But unlike the other ones that sort of hardened underground over time, this one hardened at the surface. Something happened to where the lake shrunk, maybe, or it got warmer for a few days or a few years, and the top layer of mud on this particular slab cracked, just the same way you'd find mud cracks in a drying pond or something else. So it was really neat to be able to like see these cracks, measure all of them, and compare all their angles to mud cracks on Earth, and figure out that these mud cracks probably formed in a single day on Mars. So it's kind of cool to me. What we're seeing here, one day there was a lake, the lake receded for whatever reason, and in one day the mud cracked, and then it got buried, kind of like, the mosquitoes in the Jurassic Park. And if the right conditions happen, just bury it quickly and preserve it, and 3 billion years later, we just study it. This shows some cracks in the ground that are filled with these white minerals. This is also a pretty common thing you can find on Earth, where the rock that formed most of what you see here, in this case the lake sediment, was buried then cracked, and then groundwater circulated through those rocks. The groundwater had a bunch of chemical salts in it that then precipitated out on the walls of the cracks and filled up those zones. And this is calcium sulfate, gypsum, or other types of calcium sulfate, form these ridges, which basically are just the minerals that formed in ancient cracks. And now as the whole rock is eroding, the crack forming thing is kind of sticking out of the surface. So what's neat about this is it tells us that not only were lakes there for a long, long time, we think millions or tens of millions of years to get the 1,000 feet of lake deposits, but after the lakes were long gone and that mud hardened into rock and fractured underground, then groundwater was still circulating through them, still maintaining a habitable environment for some, much longer period after that to allow all these minerals to form. So not only was Mars habitable for the lakes, but even a habitable lakes when there was groundwater. So, starting to wrap things up here, Mars was once wet. Was it warm? We think it probably was. We don't still have like the smoking gun evidence for that. But when you start talking about lakes that survive for millions, tens of millions of years, you probably do need something like a full weather system that can evaporate water from a lake or ocean somewhere, and then have clouds in the atmosphere that bring it down and precipitate and recharge the streams that kept the lakes going for millions and tens of years. Just your errant volcano going off won't provide the continuity that we see at Gulf. So we think we different and sustained in a different way. So we think.